Does it work? Okay, thank you. Thank you, everyone. Given the fact that this is algorithm sessions, we really want today motivate the use of Yang Mills theory for our near-term variational tools, believing that this can be a really fruitful environment. Setting the stage, contemporary lattice gauge theory still struggles with performing those fast, scalable, and accurate simulations of scattering processes, exemplified graphically here by the beta decay on the right, which are typically hard to compute, therefore put on a lattice, and then with hopes to predict the running of the coupling, the emergence of different phases depending on the system's energy, etc. Mathematically, we typically distinguish between two pillars of gauge theories. On the one hand, the abelian ones, which, like Z2, U1, they have been studied rigorously, become very interesting in the presence of matter, and have been implemented on quantum simulators already a lot. On the other hand, not so much attention has been given to the non-abelian groups, albeit their relevance for the standard model, like the weak interaction being described by SU2, therefore relevant for those processes like the beta decay over here. So we want today focus on those. And also note that these theories are also non-trivial in the presence, without the presence of matter. So for the purpose of this talk, as a first test case, we could also just say, let's look at the exchange particle in and of itself without the matter. If one, for example, is interested in the propagation, one would look at the two-point correlator, or space-time propagator, where a particle is created at T1, destroyed, decays at T2, and in between travels through the vacuum. The vacuum of an interacting theory, so that corresponds to computing the ground state of a Hamiltonian, a hard task, and today we propose using the VQE for that purpose. That means, of course, we have to look at the Hamiltonian and the kinematical Hilbert space. This is the wave function of SU2. So on every spatial link lives a group element. And with SU2 being three-dimensional, for example, you imagine three quantum numbers on every edge. And with a number of lattice growing polynomial with the whole lattice, we are quickly faced with the question, how do we deal with and how do we simulate these large number of quantum degrees of freedom? And the proposal in this talk today is that we say, let's restrict our attention to the gauge-invariant part of the Hilbert space. Yeah, recalling this is the part of the Hilbert space in which the Gauss constraint is implemented. And mathematically, how does this work? Let's look just at one edge in our lattice, three quantum numbers, J, M, N, J being the label of the irreducible representation of SU2. And the Gauss constraint induces this unphysical gauge transformation, which on every vertex rotates by an SU2 element our wave function. Those are unphysical. We don't want that our state changes with them. So we ask, can we do something? And there exists a possibility, the so-called spin network function, where on every vertex one inserts such an SU2 intertwiner, iota pi. This object is invariant under SU2 transformations, making therefore the whole wave function invariant. And not only does this implement the Gauss constraint fully, but also since we now contract over those magnetic quantum numbers, we see that now every edge now only depends on this label J. So in total we reduce drastically the number of quantum degrees of freedom of our system by going to this gauge-invariant Hilbert space. So that's very helpful in leveraging. And we can, of course, now express every operator that is physically on this gauge-invariant Hilbert space. For example, the Hamiltonian. In this space is decomposed into two parts. The one is the electrical part, which becomes diagonal. This is nice. We have full analytical control over it. And it's coupled to the interacting part, the plaquette part. That adds these local plaquettes in the gauge theory. And that creates sort of interactions in the theory. Not just any excitations, but excitations in a very peculiar way, namely in such a way that they obey sort of the symmetries of these SU2 intertwiners. So it has a very peculiar form, and we should keep that in mind when it comes to the question of how to find the ground state. We do the typical VQE. You've heard this already a lot. There's an ansatz. We prepare the ground state, average over it to hope to find the minimum, meaning that we have then prepared the ground state. And of course, everything depends on the ansatz, and that should be, in a clever way, sort of be motivated by the choice by the Hamiltonian we're working with. What do I mean by that in this case? You are very well familiar with the typical hardware-efficient ansatzes, where one has these dense layers of C-naughts interwoven with single qubit rotations, each with their own theta parameter. We propose to replace this, because this very easily runs into the barren plateau problem and so on, by a less dense ansatz, which has these more complicated multi-qubit gates, however, far less optimization parameters. Quickly note, every J of our lattice is a bosonic quantum number. Therefore, we need to introduce some cutoff. Yeah? For example, we could use 2 qubits to describe one J cutoff, but that would give us an explicit form of the V and W operators here in such a way that they pump sort of always gauge-invariant excitations into our system. So making sure that at all time the states created are are physical. Yeah, okay, you can think of about an adapt wiki where you do this for as long as you want. And at some point, therefore, sample the full gauge-invariant Hilbert space. So that sets the stage for our VQE. To reiterate, therefore, again, the main part of this, the main claim of this talk, we think that there are some scaling advantages for lattice gauge theory. On the one hand, the well-known things, the Hamiltonian is highly symmetric. If you impose translation and rotational invariance, you have a chance to reduce a lot your optimization parameters. The Hamiltonian is local. Lattice gauge theory is every lattice theory. We know that. That means we have sort of an expecting of a mild scaling if we decompose our Hamiltonian in terms of Pauli strings. And since these local plaquette terms, many of them commute with each other, we expect that there's a lot of parallelizable readout upon scaling. The new part in this talk is now really this proposal. Let's go to the gauge-invariant Hilbert space by implementing the Gauss constraint, because we see that there's two effects. One, it reduces again drastically our number of qubits, And second, it also reduces the optimization parameters for the state preparation. So now we want to see all of that in action. So for the second half of this talk, let's look at a small toy model where we can see all of that, or at least the second part. And the toy model I propose is the following one. We take one vertex with in 3D, 6 edges meeting at it. We impose periodic boundary conditions. So physically, you can think of it as imposing all the translational symmetries of your system before quantization. It's like the most coarse-grained system you can think of. And we do the game now. We go to the gauge-invariant Hilbert space. We identify a superselection sector in which our Hamiltonian eigenvalues lie. And we see that it means we can characterize our Hamiltonian, our vacuum state by just 3 quantum numbers. That is nice. Regarding our cutoff, that means we can use 6 data qubits, 1 ancilla, in order to describe this full toy model system. And this is good because we can, as the small system, we can completely emulate it classically, and we can also classically study our quantum computer simulating it. It means we have full control to see how our VQE really behaves. Turning to the VQE, we had already this discussion. There's the Hamiltonian. There's 2 parts coupled by this parameter G, our coupling parameter. And this G, depending on what value it takes, it really tells you about the different phases the theory can be in, right? The energy scales is sort of related to. G equals 0, that means you have just the free part of the theory remaining. But as you increase G, you sort of crank up the coupling strength of your system, and that means you will insert correlations into your system. Of course, if the system is more correlated, we expect that our vacuum needs more of these excitations to describe really what is happening. And since our algorithm is devised in such a way that it pumps these excitations, gauge-invariant excitation, into the system, more coupling will mean we should sort of consider a deeper algorithm. Give you an example. We could sort of say, hey, how many excitations do we pump into it? That corresponds to the number of 2-qubit gates and also the number of optimization parameters. We need longer algorithms, of course, needing more of these resources. However, the main comparison we wanted to do was to the hardware efficient one, which of course has less 2-qubit gates, but a much bigger number of optimization parameters. So here we really win by a lot. Now let's see how this all really compares in an ideal setting. So if we were to simulate this whole system, we see what we expect, that with increasing the coupling strengths, if we look at the error, so overlap of the prepared state to the true ground state, the error, if we want to have really low ones, we should use the deepest algorithm, which enables us to have a sub-percentage regime. So that's really nice. And the shorter algorithm still performing really well in the mid to low coupling regime. So also here really nice. But this is of course ideal simulations. Normally nothing is ideal. We have noise. And once you induce noise in the system, you have sort of this antagonistic influence, right? A 2-qubit error means you want shorter gates. We want for more accuracy the deeper algorithm, so they fight against each other. We devised sort of an a priori estimate to help us identify the best performing circuit for a given 2-qubit error of the system. And then we can use this corresponding circuit to prepare really our ground state on a given QPU, in this case today on an emulator, and then we can do some physics with it. turning back to the really beginning of the talk, we said an interesting quantity in this SU2 theories are the propagators, the two-point correlator functions, for which you use the vacuum to compute that. And indeed, if you do that, you find that there's a non-trivial correlation between the different directions of the lattices. So this is really interesting. And it looks as follows. It really, so we emulated this now with 2-qubit gate error of 0.5%, sort of realistic devices. And we see, yeah, there is an uncorrelated phase, a correlated phase, separated by phase transition, and this is really nicely described even by the short algorithms, qualitatively at least. So, summarizing, we propose implementing the Gauss constraint today that would make really this non-abelian lattice gauge theories accessible to tools like VQE, reducing both qubit number on optimization parameter numbers. We studied a small vertex test model, toy model to look at this with SU2 Yang Mills Theory vacuum, both an ideal and noisy environment, and saw that things like phase transitions can actually qualitatively be described with nice accuracy. And the next step, once our devices in our laboratories become online, we look forward to really implement this in Z2. Thank you very much for your attention.